Everybody, welcome back to another fun and exciting geometry class. Today we are going to be talking about the hypotenuse and the leg of a right triangle. Hypotenuse leg of the right triangle. And this is theorem number 12. I am on page number 83. Page 83. And what we're going to do today is actually cover this lesson, which is 2.15. And we're going to start on lesson 2.16 as well today. I'll finish 2.16 in a second lesson. 2.16 is quite a lengthy lesson with several different theorems. So let's go ahead and look at page 83. And we are going to cover theorem number 12. Theorem number 12 says, two right triangles are congruent if the hypotenuse and a leg of one are equal respectively to the hypotenuse and a leg of another, again, right triangle. So, what are we talking about here? Well, let's go ahead and look at this. What happens if we take a right triangle and I'll put one like this, and then we have another right triangle over here. Now, again, I want you to think about this, kind of the idea of postulate number 5, and what that means is you can take that shape and freely move it and turn it in space. So what if we take that shape, lift it, move it, turn it, and make it look something like this? Is not all right. We're gonna go with that. Well, you know what, we're not. I'm gonna try it one more time, and that's fine. I'm gonna go with that. Okay. Now, the idea there is, okay, first of all, they're not perfect. Okay, I know. But the idea, and you can see it in your book, the idea is that we took the triangle that was turned the other way, and we flipped it, we spun it, we moved it, and we put it next to the other one. And now what we've created is we've created a triangle next to a triangle, and we've created one big triangle. So basically, we took two triangles, this one, okay, and this one, and we put them together, and what we've done is we've created a big triangle. Now, maybe you remember when we did isosceles triangles. When we took an isosceles triangle and we cut it with a bisector, what did we do? We made two right triangles right here. So what we've, in essence, done is we've done that backwards. Okay, now we've taken the two right triangles, joined them together, and we have created an isosceles triangle. Why? Because in the given, we already know that the right angles are equal. In the given, they said the hypotenuse is equal, okay? And then they also said that a leg was equal. Now, that could be either leg because you could turn these either way. And so you could stack, if you wanted to, you could stack these sides on top of each other. What we're going to find out, though, and maybe you remember this from when we did the isosceles triangle, that because this is a bisector, then these ones also end up being equal. And we're going to get to that in just a second. But this is the idea of theorem number 12, HL, hypotenuse, there it is, leg. And obviously we have an angle as well because it's the 90, it's the right angles. So that's hypotenuse leg. I'm not going to talk a whole lot more about it, to be honest with you. We'll go over corollary 12.1, and then we're going to kind of move on. I just wanted you to see it. I wanted you to kind of understand the concepts, but we're not going to go through any proofs or exercises with this because I think you've all kind of got the idea from when we did it with the isosceles. We're just doing the opposite, the converse. Okay, Theorem, corollary 12.1. And this is on page 84 if you're following along, page 84. 12.1, the perpendicular from the vertex to the base of an isosceles triangle bisects the base and also the vertex angle. So as soon as we prove HL, then we have, obviously we have congruency, and then we have corresponding parts of congruent triangles are equal, CP, CTE. So now what we can do is say, okay, well, if those are equal, then these are equal, and that's what I just did a second ago. Then these are equal, and then these are equal. So by deduction, so what we've been doing by proof here, let's look at what we have. Well, what we have is Watch this. If I have an equal angle here and an equal angle here, and I have a line right here, what do I have? I have an angle bisector, okay? And so if I have an angle bisector, then what I end up with down here is I end up with this line also bisected, because we learned that in isosceles triangles. We've bisected this line with a perpendicular bisector. What does that mean? It means everything's equal. All right, so once we prove that, corollary to 12.1 would basically say that, then we have bisected this angle, and then we end up with the corresponding part, so everything is equal. All right, so that is all I have for you on lesson number 2.15. Let's go ahead and look over real quick to 2.16, page 84. 2.16. I'm going to cover here Theorem 13 and Theorem 14, and then we will come back and I'll do another lesson on the rest of 2.16. But 2.16 has like 4 theorems or something like that, so maybe more. It might be 6. It's got a bunch of them, but we'll get to them, okay? So don't worry. Right now, today, in this lesson, all we're doing is 13 and 14. So, talk about it. What is it? Theorem number 13 says, if one side of a triangle is greater than the second side, the angle opposite the first side is greater than the angle opposite the second side. Okay, so we have 2 triangles in this case, and it can be whatever kind of a triangle. I'm just going to draw my own. Okay, so let's go ahead and label this thing. Let's put this, we'll give this one the letter A, this one the letter B, and this one the letter C. So in our given, let's say that obviously you can see it, but BC is greater than AC. And now we can see it on this one. It's obvious that this one is bigger than this one. It just looks bigger. But let's say it's not obvious, or let's say, well, obviously we need to prove it every single time that we have something like this, because we don't have a ruler and we don't have a protractor, so there's no way to prove it measuring. So we need to prove it using other means. So how could we prove this? How could we prove this theorem? And what does the theorem say? Okay, I think this will help you if I call this the first side, okay, because this is the first. It says that the first is greater than the second. Okay, so that's what it says in the theorem. So I'm going to call this the first one. This is the BC. This is the bigger one. And then this is going to be the second. So what the theorem says, if you look over there at theorem number 13, it says that the angle opposite the side of the first, what does that mean? The angle opposite. So in this case, it would be angle A, okay? So it says that angle A, that's the angle opposite, so angle A is greater than the angle opposite the second side, or angle B. Okay, that's what the theorem is saying. Why is it saying that? Well, we can see that. Okay, in this one I drew it so that it was obvious to your eyes. Now it's not always going to be obvious to your eyes, but in this case it is. So let's take a look at how we would determine that, or what's one way that we could determine that. Okay, so if you look down there in the proof, what they do, and I'm not going to necessarily go through the whole proof, but what the idea is that they go here and they say, okay, let's take this piece right here, let's take this AC piece, and let's construct that AC piece over here so that we make an isosceles triangle. I'm going to try to get it close. Or in other words, so that our AC right here is, and we make an isosceles triangle with this right here. How did we do that? Well, we constructed an equal line segment. So we made this line equal to this line. And we could call this point D. That's what they called it there in your book. And so now once they do that, then they say that, okay, we have this angle equals this angle. So in other words, the CAD angle equals the CDA angle. Okay. Now, it's a little bit of a complicated proof, but the idea is that these two are equal. Now, because of that, you would say that the BAC, so this one, BAC, this angle is greater than, so BAC is greater than what? CAD. CAD. Why? Because the whole, the big angle, is greater than the sum of its parts, the small angle. So it's greater than CAD. Let's call this angle, I think in the book they call it angle Y, and then this angle X over here. And so you could say that instead of CAD, you could say angle Y. It's just a little bit easier to say that, okay? All right, so now what? Now what they do is they go over here and they focus on this side. Because what is this here? Well, this X now becomes an exterior angle of this small triangle. Look at this triangle right here, okay? And so X becomes an exterior angle. And so what is the rule that we learned about exterior angles? We just learned this a couple lessons ago. And that is that an exterior angle of a triangle is greater than opposite either interior angle. And that was Theorem 5. So that's a few lessons back. But if you go back to Theorem 5, it says that an exterior angle of a triangle is greater than either opposite interior. So this is an opposite interior. And so we could then say from this that X is greater than B. So in this case, X is greater than B. Okay. And now what we know from that with substitution and doing some other things, then we would know that BAC is greater than B. BAC, this one, this big one, okay, is bigger than this one right here. And like I said before, we could have gone through that. We could have looked at it with our eyes and we could have said, oh yeah, that's bigger. I can see it. But we can't do that in geometry. So we got to logically work your way through it. You say, wow, Mr. Steve, that's a complicated proof. I know it is. All right. You won't have to do anything like that on your quizzes and tests. But I want to show you that so that you can see the logic, the progression that Euclid used as he worked his way around these triangles, trying to prove different things about them. So that's Theorem 13. What do you need to know about Theorem 13? Really, none of this that I just wrote, okay? None of that. That was to help you understand Theorem 13 just a little bit more. Here's what you need to know. You need to know what it says there, that if it is, let's kind of go back to this triangle here just a little bit, and let's erase some of this stuff. And so let's talk about what do you need to know, okay? Here's what you need to know. You need to know that the angle opposite the first side, the longer side, okay, this could also say longer. The angle opposite the longer side is bigger than the angle opposite the shorter. And so this would be, let me get rid of some of this other stuff down here. So then this would be over here, this would be smaller. Okay, that's what you need to know. The longer side has an opposite bigger angle. The shorter side has an opposite smaller angle. Okay, so that's the important part. That's the takeaway from Theorem 13. Okay, I told you I'd do Theorem 13 and then 14, and then we'll be done with this part of the lesson, and then I'll come back later. What's Theorem 14? Well, it's the opposite. It's the converse. If one angle in triangle is greater than the second angle, then the side is longer. So in other words, we're going back here to this, and now we're focused on the angle. So if I say, okay, angle A is greater than angle B, okay, and that's what we have. So we have A is bigger than B, and you can see that. It's visually something that you can see. So then Theorem 14 says then the opposite side is going to be longer than the opposite side of the smaller angle. It's going to be shorter. That's what Theorem 14 says. So it's the converse of Theorem 13. Okay? All right. Well, I know that was somewhat of a complicated lesson, but I think really the core, the key there at the end, hopefully you were able to see it as it kind of came together. And that's all I got for you. We'll finish this lesson next time. All right. We'll see you later. Bye-bye.